There are tens, if not hundreds, of commercial companies and academic labs that are in the process of developing a new generation of computers, which is quantum computers. There are certain things that these future quantum computers will be able to do much faster than existing classical computers. The two quantum algorithms that are relevant for security are Shor's algorithm and Grover's algorithm. Shor's algorithm allows quantum computers to factor large numbers into prime factors and also to compute the discrete logarithm of large numbers very efficiently. The speed up is exponential, which means that a problem that would take a classical supercomputer millions of years to solve could take minutes, maybe even seconds on a quantum computer. Grover's algorithm allows a quantum computer to search unstructured data, for example, to do a brute force key search very efficiently as well. But in this case, the speed up is only quadratic, which is far less impressive. Now, the quantum computers that actually exist today are not yet large enough nor reliable enough to actually execute Shor's algorithm or Grover's algorithm. We'll need more research and more development before so-called cryptographically relevant quantum computers will become available. The expert estimates on how long that will take vary widely, but in general, the consensus is that the so-called Q-day will happen somewhere between 2030 and 2035. Even though cryptographically relevant quantum computers will not exist for several years yet, it is already important to start implementing post-quantum security today because of so-called harvest now, decrypt later attacks. You should assume that governments and criminals are already recording your IPsec traffic today, and they will be able to decrypt it several years from now once they get access to a quantum computer. If your application is something like financial or medical or critical infrastructure or government or defense or even just high-value intellectual property, then you are probably exchanging data today that must remain confidential for more than a few years. This brings us to the question, what specifically is quantum vulnerable in IPsec and how urgent is it to fix it? There are three parts of IPsec that are quantum vulnerable. 1, key agreement. 2, certificate-based authentication. And 3, symmetric encryption. IPsec key agreement currently uses Diffie-Hellman, or maybe elliptic curve Diffie-Hellman, and both of these can be broken by quantum computers using Shor's algorithm. Certificate-based authentication uses digital signatures and certificates, which currently rely on RSA or elliptic curve DSA or Edwards curve DSA. And once again, all of these can be broken by quantum computers, once again using Shor's algorithm. And finally, all symmetric encryption protocols, including AES, including triple DES, including every symmetric encryption protocol, is somewhat vulnerable to attack by quantum computers due to Grover's algorithm. Now, having said that, the severity of the threat and the urgency of fixing it is quite different for each of these three categories that I covered. Making key agreement quantum resistant is the top priority. You should literally start doing that as soon as possible. The reason for that is that this is the part of IPsec that is vulnerable to harvest now, decrypt later attacks. Also, as we will see in a couple of slides, making key agreement quantum resistant is the area where the standardization process is mostly complete, where most IPsec vendors have already implemented the software. So this is the part that's most ready to go. Making certificate-based authentication quantum resistant is the second priority. The reason that the urgency is lower is that, unlike key agreement, authentication is not vulnerable to harvest now, decrypt later attacks. Any quantum attack on authentication requires a man-in-the-middle attack and must happen in real time. It cannot happen after the fact. So for that reason, you can afford to wait fixing the authentication part a little bit until we are closer to actually cryptographically relevant quantum computers being available. Another reason to wait in this area is that the standards and the products for quantum resistant public key infrastructure are way more complicated and far less mature. Making symmetric encryption quantum resilient is the area of least concern for two different reasons. First of all, because Grover's algorithm only provides a quadratic speedup, it can easily be solved by doubling the key sizes. Now, the only minor issue here is that there's currently no standard for AES 512. The other reason for being less concerned here is that unlike classical brute force attacks, which can easily be parallelized, it appears that Grover's algorithm is not easily parallelizable. So it's questionable somewhat whether Grover's algorithm will actually be able to reach a quadratic speedup in real life. In addition to the technical arguments for implementing quantum-resistant security, there are also some regulatory considerations. The previous United States government has issued both a memorandum and an executive order requiring government agencies to implement PQC as soon as possible and to include PQC as procurement requirements under certain circumstances. And NIST has published a draft report, which is close to being finalized, deprecating some quantum vulnerable algorithms in 2030 and disallowing all quantum vulnerable algorithms in 2035. And it includes all of the algorithms that I've mentioned so far: Diffie-Hellman, RSA, elliptic curve Diffie-Hellman, elliptic curve DSA, all of them, all of the asymmetric algorithms. Other governments in other countries have published similar requirements.